Welcome guys to this new video, which is basically about design of reinforced concrete basement wall. Basement wall is a type of retaining wall, but it differs from the ordinary or the typical retaining wall in a sense that it is supported on two sides, at the top as well as at the bottom, and the lateral earth pressure is also different in this case. Basement walls. It is a common practice to assume that basement walls span vertically between the basement floor slab and the first floor slab. Okay, in the retaining wall, for example, this is the retaining wall, there is no sense of first floor slab, so it is always a cantilever in its behavior, right? But the basement wall, there is a floor slab, first floor slab right here. So two possible cases of design should be investigated for a basement wall. The first one, when the wall only has been built on top of the basement floor slab. This is the basement floor slab, and you have built this basement wall, and the wall will be subjected to lateral earth pressure with no vertical loads except its own weight, and the lateral pressure from the backfill is allowed, and in this case there is no vertical pressure or vertical load is acting on the wall except its own weight, and it is resisting purely the lateral load. The wall in this case act as a cantilever just like a retaining wall, and adequate reinforcement should be provided for a cantilever wall design just like in our previous video. This case can be avoided by installing the basement and the first floor slabs before backfilling against the wall. So when you install the first floor slab and then you just apply this backfill against this wall, then it will be a basement wall and not a cantilever wall. The second case is this case. See here, the first floor and other floors above first floor have been constructed and the building is fully loaded, and then the lateral pressure is applied on the wall. In this case, this wall is subjected to the lateral pressure as well as this vertical pressure, and this is called as a basement wall. The wall in this case will be designed as a propped cantilever wall, fixed at the base and hinged at the top, subjected to earth pressure and to vertical load. In addition to drainage, a waterproofing or damp-proofing membrane must be laid or applied to the external face of the wall. This is the external face, and it says that waterproofing or damp-proofing membrane should be applied. The ACI 11311 specifies that the minimum thickness of an exterior basement wall and its foundation is 7.5. So the minimum thickness of this exterior wall should be 7.5 inches. In general, the minimum thickness of bearing walls is 1/25 of the supported height or length. So if the height of the wall is, for example, 10 feet, so it should be 1/25 of that 10 feet, or the length of the wall, whichever is shorter, or 4 inches. Now we are going to solve an example on this basement wall. It says that determine the thickness and necessary reinforcement for the basement retaining wall shown in figure 1. Figure 1 is on next slide. This is the figure 1. You can see that there is a basement slab which is 1 feet in thickness, and there is a first floor slab which is 3-inch thickness. The height of the basement wall is taken from this point, which means that the basement slab has been ignored. So the height of the wall is 10 feet, which is from the face of the basement slab to the upper face of this first floor slab. Okay, it is this 6 inches are included in this 10 feet. So the total height of the wall is 10 feet. Now given is the weight of the backfill, which is 110 PCF. Angle of internal friction is 35 degree. Material properties are concrete has 3000 and steel has 60,000 strength PSI. Coming to the solution, the wall spans vertically and will be considered as fixed at the bottom, just like we discussed previously, and propped at the top. Okay, so consider a span of 9.75 feet, as I told you that this 10 feet includes the thickness of this slab. So we are taking from the center of the slab, which will be 3 inches. So we deduct this 3 inches from this 10 feet and we will get 9.75 feet. Okay, as shown in figure 1. For these data, the different lateral pressures on a 1 foot length of a wall are as follows. We are considering 1 foot in the perpendicular direction, right, the third direction. We are considering a 1 foot strip. For an angle of internal friction of 35 degree, the coefficient of active pressure Ca is 0.271. The horizontal earth pressure at the base is putting in this equation, the horizontal pressure is CAW into H. W is given, which is 110. H is also given, which is 10 feet. Then the horizontal pressure is 0.271, which is Ca, into 0.11, which is the weight, and 10 is the height. So we got 0.3 KSF. And when we convert it into HA, we just multiply this with the 10 by 2. So 0.271 into 0.11 into 10 into 10 by 2, because it is the, when you see here, the area of the triangle. Okay, so that's 1.49 kip per feet. Now HA acts at H by 3, as I already told you that it is a triangle. You can see here, right, that HA 1.49, right, and it is acting at 1/3 of the distance from the base. So the HA, the lever arm is 3.33 feet from the base. An additional pressure must be added to allow for a surcharge of about 200 psf. We have calculated the lateral earth pressure due to the backfill. Now we are talking about surcharge of 200 psf. And in the design of cantilever retaining wall, we already discussed that the surcharge, due to surcharge, the pressure is acting in a rectangular manner. So this is due to the surcharge. We are taking its load as a pressure as a 200 psf and finding the height of surcharge with this pressure. So dividing 200 by the unit weight, we will get a height of 1.82 feet. Now putting the same equation, just like we did it for PA and HA, we will get PS and HS, which is representing the weight, the pressure and head for the surcharge, right. So here you can see that 0.054 KSF, and we just simply multiply it with the 10, which is the length or height of the wall, because it is the rectangle, right. So the area of rectangle is simply width into height. Now HS of the surcharge acts at H by 2 because it is a rectangle. Now third one we are left with is we have only considered that the soil is undrained, or it doesn't include any water. In the preceding calculations, it is assumed that the backfill is dry. See, we didn't account for any presence of water, but it is necessary to investigate the presence of water pressure behind the wall. So let's assume the maximum water pressure, that the soil is completely saturated. So in that case, PW will be unit weight of water into height of the wall, which is 625 psf, and it also acts in a triangular way. So into 10 by 2, multiplying it into 10 by 2, because half into base into perpendicular is the area of the triangle. So it gives us 3.125 kip per feet of the wall. Now it says that it is not conservative, because the maximum pressure may not present continuously all the time. Okay, so therefore if the ground is intermittently wet, a percentage of the above pressure may be adopted. You can consider 60 to 70%, 50, 40%. In this case we are assuming 50% of this pressure. So due to active soil pressure, just like here, PA is 0.3 and HA is 1.49, right. PA is 0.3 and HA is 1.49. Due to water pressure, we are taking 50% of 625, which is 0.31, and 50% of 3.125, which is 1.56, right. And last but not the least, due to surcharge, PS is 0.054 and HS is equal to 0.54, right? So we have all the three pressures and the forces, right? As presented in this figure. Now HA and HW are due to triangular loadings, whereas HS is due to uniform loading. I already explained here, this is triangular loading and this is uniform loading because of the surcharge, and these are because of the water and the backfill. 10 feet are used to calculate HA, HW and HS as applied pressure over entire wall without the base. So pressure calculation is shown above already. Now referring to figure 1 and using moment coefficients of propped beam subjected to triangular and uniform loads and a load factor of 1.6, as we already discussed in the design of cantilever retaining wall that we will use a load factor of 1.6. The maximum moment mu at A can be calculated from, please keep in mind that A is this fixed point, okay, and for the UDL the value of MA is equal to WL by 8, and for triangular loading this is WL by 7.5, right? So mu is equal to 1.6, which is this factor, HA plus HW because they are triangular, into L by 7.5, which is a factor for triangular loading, and HS is rectangular and L by 8 is the for rectangular loading, right? So when we put the values in it, we will get a mu of 7.4 kip feet, right? So we got a value of 7.4 kip feet. Now at point B, RB at 9.75, which is right here, see, at the middle of this slab RB, we put the same values and we have to find the value of RB because we don't know the reactions as of now. So RB into 9.75 because we are taking moment about point A, so RB into 9.75 is equal to 1.6 into 1.49 plus 1.56, which is HA and HW, into 9.75, right, divided by 3 because they are acting at 1/3 and the rectangular loading is acting at 1/2, minus 7.4, which is the moment at A, right? So we are taking a moment about A is equal to 0. So RB will be equal to 1.3 kips and RA will be equal to, just multiply them and we will get and deduct the RB from it. So we will get the RA value 4.44 kips. Now maximum positive bending moment within the span occurs at the section of zero shear. So assume X from top roof of the basement wall. This is top roof, right? And VU is equal to 1.3, which is this RB, minus 1.6, which is this factor, into 0.054 into X. What is 0.054? This is 0.054, the rectangular loading, right, the rectangular pressure, into X, and for triangular it is 1.6 into these triangular pressures into X by 2 because it is triangular in nature, okay, will be equal to 0 because we have assumed that shear will be 0. So at X is equal to 4.3 feet, the shear will be 0, right? Now MC, where is point C? As you can see in this figure, this is your point A, this is your point B, and this is your point C, right, at 7.6 feet. So MC will be equal to 3.17 kip, not this point, MC is this point basically, because we are trying to find the maximum moment, and the maximum positive moment always occur at zero shear, and we found that zero shear is happening at x is equal to 4.3, and therefore we are putting this value of x is equal to 4.3 in this equation, which is actually the same equation, because when you multiply 1.3 with 4.3, see it the force becomes into bending moment, and also we are using this 4.3 in the other factors as well. For example, here we use 4.3 and here we use 4.3, and this is the shear equation. When we convert into moment equation, we have to multiply it 2 times, right? Therefore you can see that here it is square divided by 2. However, here it was not square, here it is square, and here it will be a cube. For example, see, this multiplied by this will give you a cube. So we got a value of 3.17 kip fit, which is a value of positive bending moment. Now analysis is done, and we now have to design, assuming 0.01 steel ratio and 1 feet of strip. Ru is equal to 332 psi. This is the formula for Ru, don't worry. From this we can determine the value of D, which is equal to mu divided by Rub whole square root. So mu is 7.4, just like this, right, into 12 to convert it into inches, divided by Ru into B we just determined, and the minimum requirement of depth is 4.72. When we add concrete cover and half of the bar dia, we get a 6.47 inch. So the minimum requirement of total thickness of wall is 6.47 inch, and we can use 7.5 inch very easily and comfortably. So using 7.5 inch, our D will be 5.75 inches. Now on the basis of these properties, the Ru will be equal to 224 psi. The steel ratio will be 0.005, and on the basis of that, the area of steel will be 0.345 square inches. Now we have to check whether it is greater than the minimum reinforcement or not. So minimum area of steel is equal to 0.0015 BH, which comes out to be 0.135, and minimum reinforcement for flexure is 0.0033, which is 0.23. So our steel is greater than both of them, so we will use this value, and using number 5 bar spaced at 10 inch will give us area of steel of 0.37 square inches, and our design is good. For the positive moment, MC is equal to 3.17 kip fit. For that we have to find Ru, which gives the value of rho of 0.0018. When we find the area of steel, it gives 0.125 square inches, which is less than 0.23. As you can see here, the minimum reinforcement for flexure is 0.23. So 0.23 will govern, and we will use number 4 bar spaced at 10 inches, which gives us area of steel of 0.24 square inches. Now keep in mind that zero moment occurs at a distance of 7.6 feet, just like here. This zero moment occurs, right? This point is of zero moment from 7.6 feet from point B. From the top, and 2.15 feet from the base. The development length of number 5 bars is 14 inches. Therefore extend the main number 5 bars to a distance of 2.15 plus 1.2, which is equal to 3.35 feet or 3.5 feet above the base, so that it passes through this 2.15 feet, right? Then use number 4 bars spaced at 12 inches at the exterior face. For the interior face, use number 4 bars spaced at 10 inch throughout. Longitudinal reinforcement, use a minimum steel ratio of 0.002 or area of steel of 0.17. Use number 4 bar space as 12 inch on either side of the wall. Now if the bending moment at the base of the wall is quite high, it may require a thick wall slab, right? The thickness may be increased from 7.5 inch. For example, you need a 12 inch or more. In this case, a haunch may be adopted. For example, you can instead of increasing the thickness, you can provide a haunch at the base, right? Because it will design for the moment at the section exactly above the haunch. It will reduce the thickness, because now the moment here will be less than the moment over here, right? And you have to design this section for the moment here, and the height of the haunch may vary from 10 to 20 inches, and its length may vary from 10 to 15 inches. The basement slab may have a thickness greater than the wall thickness. The thickness of this basement slab may be greater than this thickness of the wall, and may be extended outside the wall by about 10 inches, and it can be extended outside this wall for about 10 inches or more as required. So it all depends upon the requirements, basically the stability requirements, and the experience of the designer and the executing team. So I hope you have learned the design. The details of the design are presented here, the reinforcement details, and on the exterior face, right, the flexural reinforcement. So hope you have enjoyed it. Please let me know in the comment section, and hope to see you in the next video. Thank you very much. Take care, and bye bye.